This gray box on the wall matches the power grid 60 times every second, and if the grid dies, it trips itself off in 2 milliseconds flat. It's the translator between your DC panels and the AC grid. Here's the problem. Your panels make DC, a flat, steady push in one direction. Your house and the grid run on AC, 120 and 240 volts, flipping direction 60 times a second. These two are physically incompatible. Get the frequency, voltage, or timing even slightly wrong, and the box either does nothing useful or fights the grid and gets knocked offline. Start with what the panels actually hand over. It's not a clean signal. It's raw, variable DC, and on a typical home string it lands somewhere around 300 to 600 volts. That number drifts all day. More sun pushes it up. Heat drags it down. A passing cloud can move it in seconds. So the voltage coming down the wire is never quite the same twice. And here's the catch, nothing in your house can use it. Your fridge, your lights, your charger. None of them run on 400 volts of wandering DC. Plug them straight into the panels and they do nothing or worse. So the box has one core assignment and it breaks into 3 tasks. First, shape that flat DC into an alternating wave. Second, make that wave repeat at exactly 60 cycles a second, the beat the grid runs on. Third, line its timing up with the grid so the 2 waves rise and fall together. Miss any one of the 3 and the power has nowhere to go. That's the whole job stated plainly. But the first task raises a question. Before you can shape the power, how do you grab the most of it? Here's where the box gets clever. A solar panel has exactly one sweet spot, a single pairing of voltage and current where it delivers the most watts. Push a little past it and the current collapses. Pull back and you leave power on the table. And that sweet spot won't sit still. Every cloud, every degree of heat, every hour of the sun moving shifts it somewhere new. So the inverter runs a hunting routine. It nudges the operating point a hair one way, checks whether the power went up or down, then nudges again, climbing toward the peak like feeling for the top of a hill in the dark. This chase has a name, Maximum Power Point Tracking or MPPT. And it isn't lazy. The box rechecks that peak many times every second. So when a cloud passes and the sweet spot jumps, it catches up almost immediately. Lose that peak for even a moment, and you're throwing away real, paid-for sunlight. On a good system, staying locked to it is worth a meaningful slice of the day's total energy. So now the box is squeezing out every available watt. But it's still flat DC. How does a box with no moving parts turn a steady push into a wave? Now the real trick. The DC coming in is flat, one steady level. The AC going out has to rise, fall, cross zero, and swing negative over and over. There are no gears in here, no spinning generator. So how do you draw a curve from a straight line? You chop it. Inside the box sit fast electronic switches, power transistors, the heavy-duty kind called IGBTs. Think of them as light switches with no moving parts that can flip on and off thousands of times a second. By flicking the DC on and off in a carefully timed pattern, staying on longer here and shorter there, the box paints the shape of a wave out of tiny slices. This rapid on-off patterning is called PWM. But flip a switch that fast and the raw output is jagged, a staircase, not a smooth curve. So the last stage is a filter, a small arrangement of coils and capacitors that smooths those hard edges into a clean, rounded sine wave, the exact shape the grid expects. Flat DC goes in one end. A living AC wave comes out the other, drawn entirely by timing. And that's the piece that finally makes usable power. But drawing a wave isn't enough. It has to be the grid's wave on the grid's beat. Here's where timing becomes everything. The grid isn't just any AC. It's a wave beating at a fixed rhythm, 60 full cycles every second. To join it, the inverter's wave has to complete exactly those 60 cycles too. Too fast or too slow and it drifts against the grid, and drifting power gets rejected. But matching the count isn't the whole story. The 2 waves also have to peak at the same instant. That alignment of timing is called phase. Picture 2 people pushing one swing, shove together and the swing flies higher. Shove even slightly out of step and you're fighting each other. It's the same for power. If the inverter's peak lands a hair before or after the grid's peak, the electricity tries to flow the wrong way, back into the box instead of out to the house. So the inverter never just sets its wave and walks away. It's constantly reading the grid's actual voltage, watching where the grid's peaks fall, and nudging its own switching to stay locked on top of them. 60 times a second it rechecks and corrects. That's the first headline number, and now you can see the machinery behind it, a wave being redrawn and realigned in real time. But locking onto the grid creates a new danger. What happens the instant the grid goes dead? Now the dangers. Normally your inverter pushes power out onto the utility line alongside the grid. But suppose the grid fails, a storm drops a line, the power goes out for the whole street. Your panels are still in full sun. Your inverter is still making a perfect 60 Hz wave. If it keeps pushing, it energizes that supposedly dead line all by itself. A line worker climbs the pole believing it's safe, and your solar is quietly feeding it lethal voltage. Your power could backfeed the whole neighborhood. So the rulebook demands the box detect the outage and cut off almost instantly, in roughly 2 milliseconds, about a tenth of a single 60 Hz cycle. This shutdown has a name, anti-islanding, because it refuses to run as a lonely powered island. The box senses that the grid's steady rhythm has vanished and slams its connection open before it can hurt anyone. It's not a bug, it's a safety switch mandated by code. And it explains something people find maddening. When the grid goes down, most rooftop solar goes dark too, even at high noon. The panels are fine. The inverter just isn't allowed to run alone, unless you've paired it with a battery that can safely disconnect an island on purpose. So follow the whole path now in one breath. Sunlight hits the panels and out comes flat, wandering DC. The MPPT circuit hunts the sweet spot and grabs the most watts on offer. The fast switches chop that DC into slices, and the filter smooths the slices into a clean sine wave. Then the box locks that wave to the grid. Exactly 60 cycles a second, peaks landing right on the grid's peaks. And it watches the grid every instant, ready to slam off in 2 milliseconds the moment the rhythm dies. Those were the two headline numbers, and now they're not magic. 60 times a second, it rereads the grid and realigns its wave. In 2 milliseconds, it disconnects to keep a line worker alive. The box you pictured as a simple converter is really a fast, self-correcting negotiator standing between two power systems that can't talk to each other, translating one into the other and refereeing the handoff hundreds of times before you finish this sentence. So it was never just a converter. It's a synchronizer that matches the grid's beat, and a safety switch that walks off the job the instant things go wrong. Next question, what if you don't want it to go dark? That's where batteries and hybrid inverters come in, and how they legally island your home during a blackout is a whole mechanism of its own. This is an explainer, not electrical advice.